So now it says now that we're to did that, so we did that a while ago. If the electric field is replaced by a uniform magnetic field into the page, predict the path of emission. So what they want us to do, they want us to take away this electric field and replace it with a magnetic field going into the page. Now we can represent a magnetic field, a uniform magnetic field going into the page by this, right? So this is our uniform magnetic field going into the page. Everybody agree to this?
Yeah.
So this is our uniform magnetic field going into the page. And we're going to have our lead object here, holding the particle, like so. Right? So we have this uniform magnetic field. Okay? So we have this uniform magnetic field, and we're going to have the 3 radioactive emissions going up like this. And again, remember, the magnetic field is going into the page. So when we have the radioactive particles moving in like this, what we're essentially having, we're having charged particles entering what? We have charged particles entering what? This is what?
Electric field.
No, we change it.
A magnetic field.
A magnetic field. Yes, magnetic field. So the man them said that we're doing that. That's what they said.
If the electric field is replaced by uniform. Okay. I missed that part. Sorry.
Right? So we have the magnetic field going into the page, right? And we have charged particles entering that magnetic field. So we have charged particles entering this magnetic field. Now, from Fleming's left-hand rule, we should be aware that whenever we have charged particles entering a magnetic field, they will experience a
force.
A force. When we have charged particles, just like when we have current, which is the movement of charged particles in a magnetic field, they experience a force, right? So the alpha and the gamma are charged particles, right? So they will experience a force. So now we can apply Fleming's left-hand rule to determine what will happen to the charged particles. Now, in this case, if we focus on the alpha particle, right? Let us focus on the alpha particle. The alpha particle is positive, right? So it will be positive charges moving into the magnetic field. Now remember, when we're dealing with Fleming's left-hand rule, we're talking about the movement of positive charges towards the negative, right? So we're dealing with conventional current, so we're talking about positive charges moving, okay? So we're going to be considering the same idea in this case. So we're going to
draw the circles, yeah?
Repeat?
We're going to draw the magnetic field lines as circles, yeah?
No, man, X to go into the page. Right? If it's coming out, it's going to be like that, right? Dots coming out if it's coming out.
Yeah, I know it's going into the page, but that I mean, if we had to draw these circles along the X there.
No. Right? So now, again, we're dealing with the positive alpha particles, right? So we can consider the alpha particles moving in the direction that we expect conventional current to move, because conventional current involves the movement of positive charge. Okay? Yes?
Yeah.
So we're going to take...
the alpha particle.
No, we're talking about alpha particle first. Let's work with alpha particles.
And the little box, the little blue dot there as well.
It's the radioactive source. It's emitting all three emissions.
Okay.
Right? So for the alpha now, we can use Fleming's left-hand rule. So remember what Fleming's left-hand rule, the thumb indicates the force that the charged particle will experience. The index indicates the field, the direction of the field, and your middle finger indicates the, what do you call it again? The current, conventional current. So now we're going to
what the right-hand rule indicates, sir?
The right-hand rule indicates the direction of the induced current for a conductor moving in a magnetic field.
I have a question.
Yes.
Are we supposed to know that we're supposed to know to use Fleming's left-hand rule here?
That is why we started out by saying that, okay, when we have a charged particle moving in a magnetic field, it experiences a force. And we know that we can determine the force on a conductor. Well, when we're talking about Fleming's left-hand rule, we talk about a conductor. Now, the conductor is carrying charge. That is why it experiences the force. So what we can say
Have in the
essentially,
background.
what we can say essentially is that whenever we have a charge, we might have a microphone clicking on the back. Whenever we have a charge moving in a charged particle moving in a magnetic field, it experiences a force. So we can determine that force by using Fleming's left-hand rule. So that is how it all ties together. Okay? So now, again, we take our right hand, thumb indicates the force or the thrust, index finger indicates the field, the direction of the field, and your middle finger indicates the direction of the current. So now, we're going to have the alpha particle going up like this, right? So the alpha particle is going up like this, so we have to ensure that we have our middle finger pointing in the direction of the movement of the alpha particle. So it's going to be going up like this, right? And the field is going into the page, so our index finger should be pointing into the page. Can we all do that?
No, I
Yep.
think you lost me.
Yes, where do I lost you? Talk to me.
What are you using to guide me here?
Are we
Radioactive
using?
source.
All right, remember, the radioactive source is going to emit alpha, beta, and gamma, right? And they're going to go up like this, straight up, right? Now, when they enter the field, they're going to experience a force depending on their charge. Now, what we're considering first, we're considering the positive alpha particle, right? Because remember, when we deal with Fleming's left-hand rule, we deal with conventional current. And conventional current involves the movement of positive charges. So we can use that idea now to help us here. So what I'm saying now is that
Start with the fingers, you know, see that part I get lost.
repeat please.
Start with the fingers, I get lost.
You know the Fleming's left-hand rule. Thumb.
Yes, but I don't know which part to put my hand on
Okay.
this.
All right. So remember, your index finger points in the direction of what?
Index finger
Right,
in
sir.
the field.
In the field. So the field is
Yeah.
going where? The field is going where?
I have no idea right now.
Come on,
Are
Christine.
we?
Come on, Christine.
Wait,
The field is going where?
I
That's
had
what-
my middle finger
The field
into
is
the
going. No,
page.
listen,
I had my feet
listen.
going
Stop,
from
stop,
left
stop.
to right.
Stop. Wait a second.
The
I'm
axe,
marking up my page. I'm marking up my page. Hold on. I'm not sure where I'm marking up the page. So what? The field is going where?
The field in my right now, I'm watching my book.
Christine,
Going
watch
from
the
left
screen.
to right.
Christine, listen to me. What they say right here. The field is going where?
Into the page.
Okay. Which finger points in the direction of the magnetic field?
The index finger.
So in which direction should your index finger point?
Into the page.
Okay, good. Now, what we're saying now is that the alpha particle is moving up, right? It's moving up like this, straight up. So which finger points in the direction of the current?
Was still current. My middle finger.
So in which direction should your middle finger point?
Left.
No, we said that it's going up. So which direction should your middle finger point?
I have my index finger into the page right now. My thumb facing downwards and my middle finger facing the left.
All right, stop right there. Don't focus on your thumb as yet. Because the thumb, we're looking for the thumb last. We need to identify the field as well as the current. So remember, when we have alpha particles moving, that's like conventional current flowing. So the alpha particle is going up like this, so we can consider that the conventional current is also going up. Yes?
Okay, if you say so.
No, Christine, it's not about if I say so, it's how the thing goes. All right? So just open up your thinking and just let's get the thing going. So we have our index finger pointing into the page, yes?
Mm-hmm.
Because the field is going into the page. Now
Right.
the current is flowing up. which finger points to the current, to the direction of the current?
The middle finger.
Middle finger. So in which direction will you point your middle finger?
I'll tell you, lost me. My fingers still listen to you.
Christine. Listen, the current is flowing up. Yes?
Mm-hmm.
The current is flowing up. Which finger points in the direction of the current?
The middle finger.
So if the current is pointing up and the middle finger points in the direction of the current, in which direction will your middle finger point?
I don't know.
Can somebody help out, Christine?
Which she last with?
No, listen to the question. Listen to the question. The question is
The
the
middle
current.
finger point up.
Say that again, Tajay.
So my dad said the index finger with a point away from your which
No
is
man.
feel.
Tajay, listen.
The middle finger with a point up.
Go over about the thing, Mr. Roberts.
Yes, I'm gonna go over it again. So Tajay, walking, right? So the field is going into the page, and your index finger will point in the direction of the field.
Yes,
So your
sir.
index finger will point where?
So
Away.
If the field is going into the page,
No?
the point away from me, sir.
right, and go into
Away?
the page, right? Say into the page, so we
Yeah.
have the same terms.
And then the middle finger with a point up.
Right, because the current is going up, because you have the alpha
Straight up,
particle
yeah.
moving up. Right?
Yes, sir.
So as a result of that now, in which direction does your thumb point?
Towards me.
Sir, to the left.
To the left, absolutely. Christine? The thumb indicates the force that the charged particle will experience.
So the thumb indicate the force. The
Right?
index finger indicate the
Field,
direction.
of the field, direction of the field.
Yeah, and the middle finger indicate the current.
The current, right. And remember, it's conventional current. So that is why we're talking about the positive alpha particle. Because when you're dealing with conventional current, it is the movement of positive charges. Okay?
This left-hand ruling.
Yes, left-hand rule.
So and then for the Fleming's right hand rule, sir, the thumb indicate the
The movement of the conductor.
movement of the conductor.
Right, the movement of the conductor. And the field and the current are represented by other fingers.
The field and the current.
Right, the field is by the first finger, which is your index finger, and the current. The direction of the current is by your middle finger.
Okay, and
Right? So the field and the current
right
remain
hand
the
rule,
same.
sir.
The field, remember, the field and the current remains the same. It's just that for the left hand, the thumb indicates the force, while for the right hand, the thumb indicates the motion.
Motion.
Right.
Right, sir.
We have our three fingers, the thumb, index, and the middle finger at right angles. Right? So you just place them at right angle. The field is going into the page. So your index finger must point into the page. Then it says the current is going up. So you're going to turn your hand to ensure that the field is still into the page and the current is going up. So your index finger must be pointed into the page and your middle finger must be pointing up.
How am I supposed to know my middle finger is supposed to be pointing up?
Because the
Stop
child,
laughing. I tried to be serious when you make them laugh.
no, but I tell you that from before that the chart. Look, this is the source, emitting the emissions. This is going upward, so the alpha particle must be going up. Alpha, beta, and gamma will be going up.
Mm-hmm.
That is why you point your finger up, because the particles are moving up.
Point which finger up?
Middle finger.
Middle finger up.
Yes. Okay.
So
Right. So which direction does your thumb point?
okay, now my finger facing to the left because you tell me face the middle finger up.
Yes. So you see, it's just straightforward. So then now it means then that now the alpha particle will go
You
like
really
this.
think when I exam I'm gonna know to face my middle finger up?
Just look around the room. Look around the room and see how persons are twisting their fingers, and you will.
Suppose somebody doing the finger in the wrong direction and I'm gonna follow them.
Then in that case, you just open pray that they're doing the right thing. Anyways, so we have the alpha going like this, right? The beta now, so if alpha going like this, the beta is going to go opposite. So the beta is going to go like this, right? And then now the gamma is just going to go straight through.
What about if I just draw 3 lines at random and hope that I
Well,
hit it?
at least you're going to get one right. You'll always get the gamma right because the gamma goes straight through. So if you want to do that, you could do that as well. All right. So let's move on because we have a few more that we need to cover.